the Bernstein-Vazirani algorithm, how it is pronounced. Go. Cool. Let's go for it. I just kind of was scrolling down, but it seems, again, it seems pretty similar to Simon's algorithm. Another algorithm demonstrating quantum speedup is the Bernstein-Vazirani algorithm. The algorithm solves the following problem. Given a function, let me get a color, which takes an n-bit string as input and outputs a single bit where there is exactly one n-bit string that returns a value fs that equals 1. What is s? In other words, for each input x fx equals x, where fx equals s times x mod 2, we're expected to find s. Yeah, so they reformulated in a way that it's similar to Simon's algorithm. But then the problem is here you have a function that takes an n-bit string input, and it outputs a single bit, and there's just one input that returns a value 1. Everything else is 0. Correct? Correct. And so you gotta find what is the s in here. Quantum circuit to the Bernstein algorithm is shown below. Okay, so it's basically, it's not the same like the Simon's algorithm, but it's like the Deutsch algorithm, and it's actually using the same trick. It's using the same trick in here. So which is it's using the phase to basically flag, and again, talking about its practicality, its applicability, right? So it all comes down to the fact that we must implement that function, hard-coded ourselves, right? And if we implement it in a certain way, then we can take advantage of things like that. So this means basically the phase. So we are sort of flagging the phase of that exact value, and so because we're flagging it by giving it a phase -1, and I keep using the word phase, but I hate the word phase. I mean, this is just the rotation. So the rotation over the z-axis. That's how you in this case flag that, because basically if you do that after being in a Hadamard in a superposition that's created by the Hadamard gate, then you're not altering the probabilities of the measurement. But when you will do the Hadamard again, the one that's been flagged will actually go to the state Z, to the state 1. So you'll be able to know that. So the input registers initialize zeros. Good. Apply Hadamard to all the qubits to get a uniform superposition. We make the query QF. I'm just gonna skip over that. Apply the Hadamard on all the qubits and measure the n qubits. Will give the secret n-bit string s. Okay, so in this particular case, and what's more, you're using the fact that it's a binary, it's a binary string, so zeros and ones, and basically because of the trick with the minus here, that's what you get at the end, right? So here's an example. Where makes it until a qubit implement the, let us see step. Okay, so it's for n2 because it's then easy to see, and then let's say the input that we're looking for is 11, is 1 1, right? So and this is what you've got implemented in here, and as you can see, basically, wait a second, what this is doing is the input registers are initialized to 0, and the ancilla qubit to 1. It's a bit of a different approach. Give me a second. So you've got that. Then you apply Hadamard to all the qubits, and you've got that. So you've got that here, -1. And then for the string, the query function can be implemented like to control nodes. To control nodes. So after applying the to control nodes, so this is here, so you get that thing here. Why? Because after applying the to control nodes, I just don't like the annotation, but the idea is you apply the control nodes here, right? So the only bits that are affected are these ones. Okay, so you apply. So the trick, the way this is implemented is you, in the case where both will be 1, right? So if it's 0, 0, then that qubit stays 1. In which case, that's not what we're gonna get. Now, wait a second. I'm reasoning this the wrong way. Because I said at the beginning that's using the phase, but the actual example is not using. It's not using a phase. It's not using the rotation as a trick to get that, but it's using a different concept. So I like that because I thought it would be a bit of the same again. So why is that working? That is working because this is initialized as a 1. So I think that's the trick here, is that this is initialized as a 1, and then based on, it is indeed somewhat the phase that's used in this case to cancel certain possible states or certain possible measurement outcomes, because this is a 1. So the only way that this goes to a 0, so no matter what types of input you have here, right? So let's switch to green, right? So let's do again like the same thing. So you have 0, 0, 0, 1, 1, 0, 1, 1. So here the ancilla qubit stays as a 1. Here the ancilla qubit is 0. Here is 0. And in the case of 1, 1, it stays 1. Correct? Correct. So the trick here is that when you're gonna do a when you're now going to do a Hadamard, okay, when you're now going to do a Hadamard, in all of them, that's what you end up with, right? So you end up with it's confusing because they are coming from that type of notation here to make sure that this is distinguishable. distinguishable, right? But at the end of the day, notepad. If I take my notepad here quickly, and I say, so we've got this, right? Let me zoom in. Uber. So we've got that, and then we apply it. We apply sort of a watermark to all of them. So what you end up in this case is so what you end up in this case is with so you end up with this plus this. This, correct, and this. Am I doing this correctly? Am I doing this correctly? I don't know. I don't know. Wrong. Wrong. So this plus this, then this, then again this plus this, yeah, because that's for the second. So we're expanding this qubit, the qubit 0, and here we're expanding qubit 1, and now we're going to expand the qubit 0, which is basically this minus this. Correct. So now we apply control knots based on so now we apply control knots based on, first is based on qubit 1, 2, and then a control knot based on qubit. I think I can apply them both at the same time, kind of. It's going to be faster. So we'll do the 1, 2, and then 0, 2, right? And this means basically that, so I just kind of copy paste the whole string. And so whenever, so this is this stays the same. This is this stays the same. And this stays the same. I think I missed something in here. Yeah, I'm stupid. I'm just stupid. I'm really stupid. So that's all the possible combinations. I don't know why I'm even thinking about this. This. But that's not true. Some of them are minus. So here my mechanism is sort of failing me a bit, or maybe I haven't really thought that through. But I think no, that's also not correct. That's also not correct. So we have that to start with. Then so that turns into that and that. Exactly. Which turns into, which then is that's failing me. That's failing me. That is indeed failing me. No, okay. I know how to this. It's like I should apply one at a time. I should apply one at a time. So that's the Hadamard for that's the Hadamard for qubit 0. That's the Hadamard for qubit 1, and that will be the Hadamard for qubit 2. So exactly. So now when I have that, it's like applying them sequentially, right? So now that I have that, so basically, now I do the same. So now this is this one here is basically this plus this, and then this guy here, the second one, is basically this plus this. Perfect. And now I'm gonna apply the third to the third qubit. So exactly, and that's how it works. So this guy is expanded by, so that's a minus, and then that's what we get. So you're flipping the whoa. Sorry. So we were talking about this exactly. So that's a minus, and this is like that. So this is the one the qubit that we're changing. Now we're gonna act on this one. So that's a minus, and then that turns like that. And now we're gonna work on this one, which is basically another minus and like that. And now we're gonna act on this one, which is basically another minus and like that. Exactly, and that's what we have now. So we have now this, and now we apply all the control nodes. So this means in this case we've got a 1, in this case we've got a 0 here, in this case stays the same. In this case it in this case, because we apply the control node twice, it goes back to 0. In this case, because we apply it twice, it goes back to 1, so nothing happens. In this case, we apply it once, and in this case, we apply it once. And now we see that, is there anything that can be somehow cancelled out? What are the minuses? So the minuses are this, 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 and this. Because now we would apply the Hadamard again to all that, and so just to make sure that doesn't get too big, I'm gonna do it the following way. So this guy turns into oh, that's gonna be big. That's gonna be big. That's gonna be too big, definitely, for this. You see, that's okay. So that definitely doesn't scale, because if I have to now, like my process, if I have to now go through all that stuff and expand it, that's gonna hurt me. It's not gonna squeeze in here. Good. So but essentially what's happening is you're getting some of those minuses in here. So my assumption is when you do the Hadamard again, some of those are basically being cancelled out. Let's try to reason that again from scratch. So what is this actually using? What is the sort of the gist of this algorithm? Is that so it's basically using the minuses in the phase in such a way that they cancel out. So you're flagging. Basically you're sort of applying the function, and therefore practically you're flagging the input that you won. So it seems like this ancilla qubit here is used to cancel out stuff in those 2 qubits up here, so that you get the right answer. That's what it intuitively does, or at least that's what I think it does. Yeah. Not gonna go through the code. Uh, okay, that's just like, no, it's like a bigger example. But here you've got, okay, so you've got an X. But I'm curious because here is another X, like an X gate, a not. Yeah, okay, that's a bigger example. Um, with 4 qubits. Okay. Mm-hmm. Yeah. So that's what. So what happens in the real devices? So you're basically increasing the probability of just getting that result, um, the one you're looking for. But that's essentially what that's essentially what it's doing. So it's using the ancilla qubit to cancel out. Because at the end of the day, what we want is the one is we want to find, that, right? So um we want to find that. So when you do that, like when you do a Hadamard on that qubit, right, you get zero so you get like 0 - 1, right? um and so I think that's the trick, because if you do the control knot on that, and here, like what you get in here, right? So it's like the 0 - 0 - 1 - 1 - 0 - 1 - 1 type of thing. And so you want to cancel these guys here. Mm-hmm. Yeah, exactly. um yeah, I see. Give me a second. Okay, so that's what's kind of happening. And you want to cancel out, so you want to cancel out these guys and stay with that like, and increase the probability of getting that outcome. So by doing it this way, so, and this is what you're going to use, right? So you want to basically um, stick that minus in there. uh, so so by applying, so in the cases where you apply, and that's a 0 - 0, in the cases where you apply um, one of the control knots, you're switching the guy back to 0. So you're switching this. I mean, mm, not exactly. So when you apply one of the so when for the cases where only one of the control knots is applied, then you end up with the following, right? Exactly. And in case that both are applied, then you end up with kind of the same again here. Mm, exactly. And that basically that basically that will basically allow you to cancel stuff. Mm, I bet that Hadamard here is not really needed, is it? Mm, But see what I mean? It's kind of, so it's confusing for me in this algorithm is that we're only measuring this here, where like nothing happens to them. Actually, literally nothing happens to them. Mm. So that's what's confusing. That's what's kind of confusing me a bit now for the reasoning, because it's like if it's two zeros and you apply Hadamard, and then nothing happens to them, and then you're applying to Hadamard again, to Hadamards again. But I guess the trick here is that there's entanglement, right? So you can't say nothing's happening to them. So you're entangling. Oh, wait a second. Huh, interesting. So you're entangling them. Uh, so you're entangling them. So that Hadamard, actually, that Hadamard, that's pretty crazy. So that Hadamard actually has an effect on these measurements, because you've basically entangled the qubits. So maybe what's happening here, that's pretty nuts if that's the case. So maybe what's happening here is you're entangled, so you only entangle them, and that's really specific maybe to that particular problem, to that particular configuration of the problem where the S is 1, 1, right? So if we would like to have another S, that's probably different. But we entangle them for S 1, 1, right? That's pretty crazy. We entangle them, sorry, I'm just freaking out, but I think that's, so you entangle them when it's 1, 1, so that when you apply the Hadamard to the ancilla qubit, right, because you've entangled them in a way, correct me if I'm wrong, that they always agree, so to say. That's pretty nuts. Yeah, but still, why would you do a Hadamard here? So you entangle them, and then when you apply Hadamard to this one, then it basically so yeah, so it basically touches the way that the so if it's pretty crazy actually. So once you entangle them, uh, 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 and you apply the Hadamard to that particular case, where this is 1, right? Which means when both of these are 1, yeah, then you're affecting those qubits as well, because you're basically saying this is only going to be 1 if this has been 1. Wow, that is actually, I think that's it. I think that's it. Basically, so in this case, you're you're using entanglement to get what you want, but not like partial measurement like we saw in Simon's algorithm. But what you're using here is you're modifying one. So you're modifying the entangled state. Yeah, but then why do you need these ones here? I think I'm gonna make a second video on this, because I think that can be an interesting case to take a look at a bit more in depth. Um, I'm in between. It's a combination of the of the minus thing, that these things cancel out each other. But I also find the explanation of applying a Hadamard on the two entanglements, right? Because it's this one entanglement and this is another entanglement. Um, yeah, yeah. I mean, maybe those hardwires are just here to correct, right? And maybe they are just needed to kind of like bring back the information to the so you can measure on the Z basis, so to say. Maybe that's something you must do anyway. Yeah. Cool. I'll give it another try.